All right, good morning. Today we're going to be taking a look at lesson 4, which is going to be talking about ion concentration. So basically, we've been talking about dissociation, taking a solid compound that is able to dissociate into ions in water. And we're going to see how those concentrations of the ions vary based on the dissociation equation. Before we get into that, we're going to do 2 review questions. The first one is determine the molar concentration of 4.25 grams of lithium nitrate dissolved in 900 milliliters. Okay, so what you are looking for is the molar concentration from a mass dissolved in a certain amount of liquid. You can pause, do the problem, and then when you're ready, you can unpause and I can walk you through the process. Okay, so let's go through this one. Okay, I'm going to be trying a new system today, so we'll see how it goes. I currently am not really good at it, so I apologize. Okay, so we're going to start with our known. Let's go ahead and write down what we're looking for. We're looking for the concentration of lithium nitrate. You're going to start with what you know, and what you know is this mass here. So let's come back here. 4.25 grams of lithium nitrate. Okay, the goal is the end units we are trying to get is blank moles per liter. Okay, so we need to get moles in the numerator, okay? We need to get rid of this grams, okay? That is nowhere near anything that relates to our goal. However, it bridges us to our goal. So we're going to use molar mass here. The molar mass of lithium nitrate is 68.95. 68.95 grams. And in the numerator, we're going to have moles. Grams cancels out with grams, and currently from here to here, we have moles of lithium nitrate. All right, perfect. So we're halfway there. We've got moles in the numerator. We've got moles in the numerator. What we're missing is volume in the denominators. We need liters in the denominator. Okay, well, we have our volume here, and it's not in the correct units. We need to convert it into liters. So we're going to divide this number by 1,000. Okay, that is the same thing as moving your decimal point over 3 times. You can either divide by 1,000 or move your decimal point over, which will then give us a volume of 0.990 liters. Now, it needs to be in the denominator, okay? So we're going to actually divide by this volume. Okay, so in your calculator, actually, before we confirm that, from here to here now, we're going to have the units moles per liter. Perfect. That's what we're looking for. So here we're going to have moles per liter of lithium nitrate. Again, I apologize for this new system here. Okay, once we plug that all in, we're going to get an answer of 0.0685. Okay, this is 3 significant digits. These leading zeros here, they do not count, okay? So you can present your answer like this. You can present your answer like this. Either way is acceptable. And one more thing, you can also write it with the capital M. Remember that the units of moles per liter is also equal to capital M. Okay? Okay, next example, again, you can pause and then we can join in going through the answer together. A water has 500 milliliter sample, a water that has some bad grammar there. Basically, a 500 milliliter sample from the Calgary water treatment plant is found to have 332 milligrams of TSD, which stands for total dissolved solids. Water must have a TSD concentration of less than 500, ppm to be considered safe, okay? So we're comparing a number here. We're comparing the information that they've given us about our water sample. Oh, yep. Does that compare and does that meet the requirements of being within 500 ppm? So like I said, when you are comparing something, it needs to be in the same units. Okay, so we need to find our answer in ppm so that we can compare it. We are looking for concentration in ppm, which is equal to mass measured in milligrams over volume measured in liters. These are the units of ppm. Okay, so our mass is already in the correct unit, so I'm not going to convert that or do anything. We can go ahead and plug that directly in to our formula. Our volume, on the other hand, is in milliliters, so we need to convert this into liters. Same thing that we did with the previous example. You're going to divide this number by 1,000, which is equivalent to moving the decimal place over 3 times. So I divide by 0.500 liters. Once I divide those two numbers, I get 664 milligrams per liter, which is the same thing as saying 664 ppm. Now, the problem doesn't end here. Yes, we have our number, but the main question is the water safe to drink? Does it meet this requirement? So, no, water, not safe. Because 664 ppm is greater than 500 ppm. So it doesn't meet the requirement. It needs to be lower. That says ppm there. This new system, it's not going so well for me. All right, let's get into today's lesson. Okay, the learning goals are not listed, but basically we're going to use our new friend, which is going to be with us for the remainder of the semester, called molar ratio. Molar ratio is a ratio between entities in a chemical reaction. Okay, so it's a ratio between products and reactant entities. That says reactants, I promise you. Okay, so basically, in a chemical reaction, we are able to use any entity, whether that be a product or a reactant, to find the value of an unknown entity within that chemical reaction. Okay? So, in a chemical reaction, aka a molar ratio. Okay, so basically, in a chemical reaction, a molar ratio, also known as a conversion, that's an S, from a known to an unknown entity. Okay, here's what I'm talking about. We will use this more, but let's say we know something, a known entity. And we want to find an unknown entity in a chemical reaction. We are going to use this thing called molar ratio to perform unit analysis. So you've probably noticed that I use this concept a lot, going back and forth between units, going back and forth between entities. We always have a converter. So our converter in this situation is called a molar ratio. I'm going to show you how to set this up. So basically what happens is a molar ratio. Actually, we will do an example first before I go into kind of the general gist of what a molar ratio looks like. Let's do this example here. It says write a molar ratio for the following reactions. Okay, so this guy here has information provided. So this is my known. Okay, my known can be any one of these four entities. It doesn't have to be the first one. And then this one here has a question mark. This is my unknown. Okay, let's just go ahead using unit analysis, see how a molar ratio actually forms. So we're looking for this guy here, the concentration of hydrobromic acid. Okay, so HBr, the concentration. Like we've been saying, you always start with what you know. So I know I have 2.9 molarity of this compound here. So 2.90, capital M, which means mole per liter, of iron bromide. Okay, iron 3 bromide. Then we need to convert this. We're going to use our molar ratio. Okay, so here it is, our molar ratio, which connects our known entity to our unknown entity. That's it. Give me 1 second to fix the arrow. Okay, to our unknown entity. So how do we actually set this guy up? I'm glad you asked. So we have a coefficient of 2 in front of our chemical reaction. So I'm going to divide by 2 moles of iron 3 bromide. Okay, and then on top we have 6 moles of hydrobromic acid. So 6 moles. Okay, just start that all over. 6 moles of HBr. Let's do some canceling out. Iron 3 bromide cancels out with iron 3 bromide. Moles cancels out with moles. And we are left with molarity of hydrobromic acid. Once you plug this in, so when you're plugging this into your calculator, you're going 2.9 times by 6 divided by 2. Once you plug this guy in, you get a molar concentration of 8.70 mole per liter of hydrobromic acid. There's your final answer. Now, if we examine the molar ratio in detail, you'll notice that in a molar ratio, you will always have the coefficient of your unknown in the numerator and your known in the denominator. Okay, so if you're ever confused and your unit analysis isn't making sense, you always want to start with your known, divide by the known coefficient, and multiply by your unknown. Okay, this is just another way of seeing it. I prefer that we write it just through strict unit analysis. Okay, let's go ahead and just do another example just to get us comfortable with this idea. So now we have this guy as our unknown. Like I said, anybody, any entity within this reaction, what is happening with my pen? Any entity in this reaction can be an unknown, and any entity in this reaction can be a known. Okay, so when I'm talking about entities, I'm talking about these reactants and these products. So I can have any one of these 4 things be an unknown, and I can have any one of these 4 things be a known. Okay, so we have information provided about carbon dioxide here. So this is actually my known. So if we wanted to find the unknown concentration of this compound here, which heptane, it would be like this. So you're going to start off with what you know. I know that I have 0.23 moles per liter of carbon dioxide. From there, we take our known and we convert it into our unknown by using a molar ratio. Okay, and like I said, this is how you set up a molar ratio. So currently carbon dioxide is in the numerator. We need to get rid of that. So what we have to do is divide by the coefficient of carbon dioxide. So we actually have 7 moles of carbon dioxide in this reaction. Perfect, that gets rid of carbon dioxide. But we still need to link to our unknown. So I look at how many moles I have of my heptane. So in front of it, there's nothing, okay? Like I said, in chemistry, ones are invisible. So there's not a 0 in front of here. If we had 0, this wouldn't even exist. We actually have this invisible 1 here. So I have 1 mole of C7H16. Perfect. The moles cancel each other out, okay? And remember that end goal, we're looking for concentration of this guy here. So I'm now, when I plug that into my calculator, I get a concentration of 0.033 moles per liter from here of heptane. That should be a 7. Perfect. So you can write it like this, or you can write it like 3.3 times 10 to the negative 2. Either one is acceptable, and you can use moles per liter as well. Yeah. Okay, so let's go through an example here. Okay, we're going to start off slow. The process of doing these problems is going to be the same. The first thing that you're always going to do when you come across an ion concentration problem is you're going to write a balanced reaction. Okay, so step 1, write a balanced reaction. Okay, let's circle that. Write a balanced reaction. Okay, so go ahead and do that. We have sodium chloride that is dissociating. Okay, so usually when we're ever doing ion concentration, it's a dissociation reaction. So sodium chloride looks like this. And then it dissociates into sodium ions, which is aqueous. Okay, that's a positive charge there. Plus chloride, which we have 1 of, and it is also aqueous. Then step 2 is to list your known and your unknowns. Step 2, list known / your unknown. I should be doing this in a different color. Let's grab red. Okay, so step 2 is going to be in red. Okay, so we have, what is the concentration of each ion if we have a molar concentration of 0.087 sodium chloride? Okay, so it's saying that we have 0.087 moles per liter of sodium chloride. Sorry, 7.1. Hold on. Let me fix it. I'll be right back. Okay, so we list our known and then we list our unknown. There are 2 things that we need to be looking for. Okay, so we're looking for concentration of Na plus, and we're looking for the concentration of chloride. I'm going to start off with 1. So let's do sodium first. Okay, so this is my unknown. I'm looking for a concentration of my sodium ions. Let's go ahead and scroll down. So step 3, let's do it in purple. Step 3 is to use molar ratio. So use molar ratio to find unknown. All right, so 0.0871 moles per liter of NaCl. Great. Now we need to get it to link to sodium ions up here. Okay, so we're going to use our molar ratio. I have 1 mole of NaCl. NaCl cancels out. And then I have 1 mole of sodium. 1 mole of sodium ions. Moles cancels out. Perfect. 0.871 times by 1 divided by 1 gives me 0.0871 moles of sodium ions. Okay, so there is my first concentration. Okay, so let's go ahead, scroll back up. So for the sodium, I have 0.0871 moles per liter. Okay, you're going to do the same thing for chloride by yourself. So what I'm trying to say is, like, when you are calculating unknown entities in your solution, you have to write a molar ratio statement every time you need to find something new in the equation. So let's say we're looking for chloride now. So I'm going to do this one in blue. You have to write a molar ratio statement again. 0.0871 moles per liter of sodium chloride. So that's this here, starting off with what I know, times by my molar ratio. Okay, so this time, same thing, 1 mole of NaCl. And then on top, you're going to multiply by 1 mole of chloride. So now we're treating it differently. For every unknown, you have to write a brand new statement. So 1 mole of Cl minus 1 times 1 divided by 1 times by our concentration. Anything is itself. So chloride would also be 0.87 moles. Okay, so from now on, I will be only calculating one concentration for each example, and you will be doing one on your own. Okay? Okay, so let's do another example. This one is asking us what is the concentration of each ion in a 0.0636 mole per liter solution of ammonium sulfate. Okay, so let's recap those steps. First thing that we need to do is write a balanced reaction. So first step is a reaction, balanced. Okay, so we have ammonium sulfate. Okay, that looks like this, NH4, and we have 2 of them because sulfate has a -2 charge attached to one sulfate. That's solid. Like I said, whenever we're looking for ion concentration, you have to write a dissociation reaction. So there are 2 ammonium, that is a 4, ions, plus 1 sulfate ion, which has a 2- charge. Perfect. Okay, we are looking for each ion. So I'm going to solve one with you, and then you can solve sulfate on your own. So the second thing you need to do is set up your reaction. So you have to list your known and your unknown. Okay, so we know that this is 0.0636 mole per liter. I'm going to do ammonium with you guys, and then you guys can do sulfate on your own. So we're looking for blank moles per liter of ammonium. Perfect. So step 3 is to use molar ratio. Remember, every unknown requires its own its own statement. Okay, so start with what you know. I know that there is 0.063 mole per liter of ammonium sulfate, NH4, 2SO4. Okay, from here, you're going to use your molar ratio. I have 1 mole of NH4SO4. I'm sorry, there should be 2 of these. And then there are 2 moles of the ammonium ion. So 2NH4. Sorry, that should say mole there. Let me just fix that. Okay, so 2 moles. Remember that number is coming from here of NH4 plus. Perfect. So in your calculator, you're going 0.0636 multiplied by 2 divided by 1, which will give me a concentration of 0.127 mole per liter. Okay, ammonium sulfate cancels out with ammonium sulfate, moles cancels out with moles. I'm left with this final answer of NH4 plus. Okay, pause and take a minute to do the other one on your own. And when you're ready, you can check your answer. So for sulfate, the concentration is going to be 0.036. Oh, sorry, it's okay, you should get 0.6, sorry, 0, oh dear. Try it one more time. 0.0636 moles per liter. Okay, what we're noticing is when something has a 1-to-1 ratio, the concentration is going to be the same. So if it has a 1-to-1, 1-to-1, 1 times 1 divided by 1, you're left with the same value as your known. Okay, so you'll notice that. But to play it safe, you can always write this statement out and to double check. Okay, you're going to try this one out on your own. So pause. When you're ready, come back. Okay, there's the answer there. If you did not get this, go through it again. Make sure that your molar ratio was not accidentally flipped. Okay, so first step, write your reaction. Second step, use your molar ratio and make sure it's correctly placed. Okay, we're going to talk about working the other way. So like I said, when you're doing a reaction, it doesn't matter where your known and unknown is. For some reason, students get very confused when they're given an ion concentration, okay? So I'm going to go through it and you're going to find that the process is exactly the same. Okay, so it's saying what concentration of solute, ammonium phosphate, would be required to produce an ammonium ion concentrate of 0.918 moles per liter. Okay, first thing you're going to do is write a reaction. Just going to grab a color here. So, first step, balanced reaction. So, it's going to be a dissociation reaction. The solute is going to dissociate. The solute is ammonium phosphate. So, that is going to be NH4. And we have 3 of these guys. This phosphate has a -3 charge. And then this is going to dissociate into NH4 plus aqueous. We have 3 of those, okay? Plus 1 phosphate, aqueous, 3 minus. Step 2 is to list your known and your unknown. So it's asking us what concentration of solute. So we're looking for concentration of solute. Perfect. Then it gave us a concentration of our ammonium ion. So 0.918 mole per liter. Okay, so that's step 2. You label your unknown and your known. Again, it doesn't matter. It can be any one in this reaction can be considered the known or the unknown. Lastly, you're going to use your Stoic statement or your molar ratio statement to calculate the unknown. So 0.918 mole per liter of NH4 plus. We're going to use our molar ratio. Okay, there is 3 moles of NH4 plus. Okay, so we get that 3 from that coefficient. And we want NH4 plus in the denominator so that we can cancel it out from the numerator here. Then we have 1 mole of NH4, there's 3 of those, phosphate. Okay, moles cancels out and I'm left with concentration of ammonium phosphate. Perfect. When we plug that guy in, you're going to get 0.306 moles per liter of ammonium phosphate. Okay, so this here is my final answer. Awesome. All right, so we've got another type of example here. So sometimes they're going to give you a mass, and you're going to have to use that mass to calculate a concentration before you can determine ion concentration. So I'm going to show you how to do this in 2 ways, okay? So let's go to method 1. Actually, we will make another video.